Okay, welcome. So last class we did a very expansive overview of how to analyze functions. So in summary, we did a recap on local and global extrema, right? So we had the local maximum and global maximum and what are the differences between those. We covered like increasing and decreasing functions and how that's defined mathematically, and how a positive derivative indicates that the function is increasing and a negative derivative indicates that the function is decreasing at that point. We also talked about extensively about cubic functions. So remember how there were three types. And some geometric properties about those cubic functions, right? We had point symmetry. We also talked a little bit about even and odd functions. So even functions were functions that were symmetric about the y-axis, and odd functions are functions that are symmetric about the origin point. We also talked about some special ratios that will be useful in cubic functions, such like the 1 to 1 to 1, right? The inflection point, the local minimum, and so on. There was also the 1 to square root of 3 ratio, where we had 1 to square root of 3, like that. And we proved it using a coordinate system that we set up like that. So we did cover a lot today. So the first thing that I want to do for this lesson is to go over some actual problems in the workbook. So we'll begin with the workbook, and then as time permits, we might go into quartic functions today. Okay. So let's see here. Number one is a proof question. So let's talk about that. If function f of x is continuous on the closed interval and differentiable on the open interval, and f prime x is greater than 0 for all points on that interval, then f of x increases on this interval, and it asks us to prove that. So we got a pretty intuitive geometric picture last time, I think, but here's a formal sort of a proof for this statement. So let's say that, let's define our interval. Let's say a is here and b is here, and this is sort of our function. Okay, so it's continuous on the closed interval and differentiable on the open interval, and f prime is greater than 0. Okay, remember the definition of an increasing function. We had two numbers, x1 and x2, and if x1 is less than x2 and f of x1 is less than f of x2, then we can say that the function is increasing, right? So what we need to do is we need to find, let's set a arbitrary x1 and x2. Okay. The setup here is that x1 and x2 are in the interval, closed interval a comma b, so that x1 is clearly less than x2. So there are two different points that we've got on the curve here. And then what we can do next is we can do this. So this proof requires us to connect two distinct points. So we got two distinct points, x1 and x2. But what it gives us is the derivative, right? So in order to get the derivative, what we can think of is we can connect these 2 points with a secant line, sort of like that. And since the conditions say that it's closed on the continuous on the closed interval and differentiable on the open interval, then we can try using the mean value theorem, right, from a couple of lessons ago. So the mean value theorem states, because we can use it since all the conditions are satisfied, that there exists a C on the interval x1 and x2, right? Between x1 and x2, so that the average rate of change, so that's x2 minus x1 under f of x2 minus f of x1 equals f prime of c. So here, in this specific example, our c would be somewhere along here, so that the slope of the tangent line is equal to the slope of the secant line. Okay, so what we can do now is we want to isolate this expression, right? F of x2 minus f of x1. So if this is always greater than 0, then we've essentially proved that when x2 is larger than x1, as we have stated here, f of x2 is going to be greater than f of x1. So let's multiply both sides by x2 minus x1. And we can do that because x2 and x1 are never going to be equal to each other, so there's no issues there. So f of x2 minus f of x1 is going to be equal to f prime of c times x2 minus x1. Okay, let's see here. We know that x2 minus x1, because we set it up this way, it's going to be positive, right? x2 is always greater than x1. And we know from the conditions that for all possible x values on our interval, f prime of x is going to be greater than 0. So f prime of c is always going to be greater than 0. Therefore, f of x2 minus f of x1 is greater than 0, since a positive number times a positive number is always a positive number. So we can conclude that f of x2 must always be greater than f of x1. So we proved that when x of 1 is less than x of 2, f of x of 1 is less than f of x of 2. And that is the literal definition of an increasing function on the interval that we defined, which is a comma b. And there you go. That is a more formal proof supported by algebra and the mean value theorem. Yeah, so that's an example of how the mean value theorem can be used in a lot of proofs. Okay, so that was more of a theoretical problem. Let's see here. Okay, so let's solve number 2 together. It asks us, for what range of real number a does this function f of x equals 1/3 x cubed plus ax squared plus a plus 6x increase on the set of all real numbers? So that means that when a function is increasing, and this is like completely differentiable and continuous, f prime of x must be greater than 0. So we need to solve this inequality. It says on the set of all real numbers. So this has to be true for all x. So first we need to find the derivative. So let's say f prime of x equals x squared plus 2ax plus a plus 6. Now, as you recall, if this has to always be greater than 0, this is a concave up parabola. That means the discriminant has to be less than 0 in order for this to not touch. Now, I don't know if I've told you this. I might have, or I might have not. You see the 2a here. Now, in your quadratic formula, let's talk about this for a second. The original quadratic formula is, as we know, negative b plus minus square root of 4, b squared minus 4ac over 2a, right? So this is for ax squared plus bx plus c equals 0. I'd want to introduce to you something called a simplified quadratic formula or an even quadratic formula. And this quadratic formula is for solving equations where the x coefficient is an even integer. well, it doesn't have to be an integer, but something that you can easily pull a 2 out of. So that would usually mean that it's an even integer. But it also works for this type of equation here, where a could be any real number. 2bx, let's call this b prime, plus c equals 0. In this case, we can just plug in b prime, 2b prime instead of b into the original quadratic, and the result is going to be negative b prime plus minus b prime squared minus ac over a. So you're probably wondering, do I have to memorize this formula? And I would recommend that you do. This really saves you a lot of time, because when you're squaring stuff using the original quadratic formula, numbers might get like pretty large. Say if you have like something like negative 16x, you would have to do 16 squared. But if you use the simplified formula, then you only have to put 8 squared in your calculation, right? So that's sort of the difference. So I encourage that you take note of this formula. And the good thing is we can actually use this part as a functioning discriminant, right? Because it acts exactly the same as the original discriminant. I like to call it d over 4, because it sort of has the resemblance of dividing the entire discriminant by 4. So we're going to compare d over 4, and this simplifies our calculations in this case too, because we can take out the 2 and say a squared minus a minus 6, right? And immediately get our discriminant. Now, this has to be less than 0. So now we can solve this quadratic inequality. This is 3, 2, minus, so a is going to be greater than negative 2 and less than 3. I hope we all remember how to solve quadratic inequalities. If the inequality symbol is facing towards the equation, that means it's going to be between the two roots. If it's facing away from the equations like this, then it's going to be less than this root or more than this root, right? So that all hinges on the principle of, hey, this is a positive coefficient, so my parabola is going to be concave up. So that means if this is your first root and this is your second root, depending on if it's less than 0, then it's going to be between the two roots, or if it's more than 0, it's going to be anywhere outside of the two roots, okay? So remember how to solve your quadratic inequalities. Okay. Side note, when you're looking at quadratic equations, and I hope you know these formulas. Okay. So when you're looking at the equation ax squared plus bx plus c equals 0, and you call these roots alpha and beta, you can get to the values of alpha plus beta, alpha beta, by looking at the coefficients, right? So alpha plus beta equals negative b over a, and alpha beta equals c over a. And you can derive all that by just plugging in the quadratic formula. There is a way to find the difference of two roots. The difference of two roots is, you can simply look at the quadratic formula again. One is going to be plus square root of b squared minus 4ac, and one is going to be minus square root of b squared minus 4ac, right? So if you're going to take the difference of the two roots, the negative b will cancel out, and this value will be doubled. So alpha minus beta, and let's put an absolute value on it, is going to be, now, we're going to subtract this from this, right? And then A, if A is negative, we need to make sure that the difference is going to be positive. So we need to put an absolute value A on that, and it's going to be square root of D, which is your B squared minus 4AC. This only works for the original quadratic formula, so you can't use D over 4 in here. So that's the only thing that I would warn you about D over 4. Because the whole premise is that we take this original quadratic formula and then we subtract it, which means we get a coefficient of 2 here, and that cancels out with the A. So the formula would look different for D over 4. I hope you can memorize at least these two, and knowing the difference formula is also very helpful. Square root of D over absolute value of A. Okay? Okay. There is an extension for this with cubic equations and general polynomial equations, but we'll cover that when we need to. Okay, so that's a note on quadratics, right? The quadratic equation and solving quadratic inequalities is the baseline skill that you need to have in order to be successful in analyzing cubic functions and beyond when you actually take a full calculus course. Because although the ideas, right, the ideas of calculus matter, all that supporting work is going to be from algebra, pre-calculus. So if you take pre-calculus 12, you have to pay a special, very, very special detail to how the algebra works and what properties does all these graphs have, okay? So that was number 2. I think number 3 is basically identical. Well, it's slightly different, right? But the premise is identical, so I'll leave that for homework. Number 4 is more conceptual, so I'll leave that for homework as well. Let's try number 5. So now we get to cubic functions. The local maximum value of function f of x equals x plus 1 squared, x minus 3 plus a is 5. So the local max value is 5. Find the value of a. Okay. So here we go. X plus 1 squared times x minus 3 plus a. Now, this setup looks familiar, right? So remember, I told you to look at this through a difference function, right? We're going to start off with this part, and then since a is a constant, we can shift the entire thing up. So our function, it's a positive coefficient, so it will look like this. Okay, the reason that we know that is because we have x equals negative 1 as a root and x equals 3 as a root. Now, the multiplicity of this root is 2, right? So we know that it's going to be tangent, and then it will break off in the same direction. And then the multiplicity of this one is 1, so it will go straight through. Now, the only way that this can happen is that the multiplicity of 2 root has to be right here. Since negative 1 is obviously smaller than 3, then 3 needs to go right over here. So every time you solve these types of questions, if you can draw the graph easily, then you should probably draw it, right? And then negative 1 is going to be over here. Okay. So this is our function. This is a. F of negative 1. Yeah, and the local max value is going to be whatever this value is, right? So f of negative 1 equals a equals 5. Oh yeah, okay, so it was already written up in the question, but a equals 5. What if I asked you what's the x-coordinate of this local minimum value? Now, what you have to do normally is you have to take the derivative using the product rule. You have to set it equal to 0. You have to solve the quadratic equation. You have to exclude -1, and then you'll get your answer. But since we know the 1-to-1-to-1 ratio, we can simply say that, hey, this is going to be 2-to-1, right? Because there's another 1 hiding here. The distance between these two is 4. So we can divide 4 by 3 and then subtract it from 3. And that's going to be 5/3. And we get it immediately just like that. This problem didn't require it, but other more complicated problems will probably require you to do more algebra, in which you can use those ratios to your advantage. So this is 2-to-1 in this case. Okay, so thinking about the logic here, why couldn't -1 go here and 3 go here? Because then the multiplicity of -1 will be 1, but we need a multiplicity of 2. So that's why -1 has to be up here, and 3 has to be up here, and then the entire thing is shifted upward by a. Or you can also think of the function as fx minus a equals x plus 1 times x minus 3. So that would literally be considering this as a difference function. But I think treating it as you set all this up and then you shift everything up by a also makes more sense. All right, number 6 would be a very similar problem, so I'll leave that for homework. Let's see. Number 7 is also pretty similar. You're given the graph, so you have to take a look at its derivative, right? Let's try number 8. Okay, a differentiable function f of x has a local maximum value b at x equals a. Find the equation of the tangent line to the curve y equals x fx at the point where x equals a. Okay, so it has a local maximum b at x equals a. So f prime of a, first of all, has to be 0, right? And then its sign has to go from plus to minus, right? Because that's what a local maximum is. It goes from plus to minus around x equals a. We don't know anything else about this function, but I think that would be fine because we're finding the derivative of x f of x. So y prime would be, let's use the product rule, take the derivative of x, that's going to be f of x, and then take the derivative of f of x, that would be x prime of x, like that. And let's plug in x equals a. So y prime of a would be, what's f of a? We know that b is the local maximum value, so that's going to be b. F prime of a would be 0, so the only thing left would be b. So therefore, the equation of the tangent line would be y equals, we have the slope b times x minus a, plus f of a, which is, we need to plug in a here. So it's a f of a, which is bx minus ab, plus we know that f of a is going to be equal to b. We should probably label that on. So ab. So that cancels out, and your answer would be y equals bx. Okay, yeah, so pretty simple. When there's a local maximum, first thing, derivative equals 0. One layer deeper would be the derivative would go from positive to negative when you go left to right from that point. Okay. Number 9. Number 9, I'll leave you that as homework. I want you to actually challenge yourselves a little bit more than we've done in the previous units and try to figure out a solution on your own. But we'll go through number 10 together. Number 10 asks us, what is the minimum value of positive integer a so that function f of x, which is given to us as x cubed minus ax squared plus 2ax plus 2 has local extrema. Okay, so we can see that this is a cubic function with a positive leading coefficient. And in this specific case, the leading coefficient is 1. So if the leading coefficient is 1, we call this a monic cubic function. Monic simply means that your highest order term has a leading coefficient of 1, okay? And this has to have local extrema. Okay, so now we know there are 3 different types of cubic functions. There's this, there's that, and there's that, depending on how many points have a derivative of 0. Which one of these has local extrema? Only this one does, right? This isn't a local extrema, right? Because the derivative does not change sign. And it keeps on increasing at near this point, right? So it goes from like that, it briefly stops, and then, but it keeps on increasing. This, it's just an increasing curve. There is no point where a local minimum or maximum occurs. So in order for this cubic function to have local extrema, we need 2 points where the derivative is 0. Now the derivative we can find quite easily, 3x squared minus 2ax plus 2a. This equals 0 must have 2 solutions, obviously, that are different from each other. If there was one solution, the curve would look like that, right? So now we can also use the discriminant, and I'll use the discriminant over 4 equals, ignore the 2, a squared minus, multiply this and that, 6a, and that has to be greater than 0 because our curve has to intersect at 2 points. So here the inequality symbol is pointing away. So we go, the solutions are 0 and 6. So a has to be less than 0 or a has to be greater than 6. And the minimum positive integer, so we don't need to care about that, that satisfies this inequality would be a equals 7. All right. So now you've got an opportunity to draw some cubic functions, see how local extrema can be found. The existence of local extrema can be found by using the discriminant. Number 11 is basically the same thing, but it is a little bit more sophisticated. So I'll leave that one for homework as well. And number 12 is a quartic function. Okay, so let's talk about quartic functions next. So cubic functions are polynomials with degree 3. So naturally, quartic functions would be polynomial functions of degree 4. Now, the geometry or the shapes of the curve do get a bit more complex than cubic functions because we are going up a degree. Usually, you will learn up to quartic functions even in like a regular calculus class, because that's sort of the limit that you can do with visual reasoning and calculations that you can do by hand. So as long as we are comfortable with degrees up to like 4, then you should be very, very nicely prepared. Okay, so the quartic function is written out like that. F of x equals ax to the power of 4 plus bx cubed plus cx squared plus dx plus e, where a is not equal to 0, or else it would become a cubic, right? Okay, so f prime of x here, right? Since we've learned that derivatives are very important ways of analyzing such functions, let's only take the derivative of the first term since that's most important, 4ax cubed plus blah, 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 right? So the derivative of a quartic function is going to be a cubic function. Now I'm going to tell you 4 types of general shapes that quartic functions have. If you go into specifics, there's like a lot more types, but I'll tell you the 4 general types. We'll assume that a is greater than 0, just to simplify our classification. Now, our base function that you might have learned in pre-calculus 12 is y equals x to the power of 4. When you're doing, like, you might have learned this in pre-calc 11 as well, when you're doing exponent laws and you're seeing how many solutions does this have, you'll probably be used to seeing sort of like a curve like that. Now, x to the power of 4 is an even function. It's symmetric about the y-axis. F of negative x equals f of x, right? The curvature is different from that of a quadratic, but the shape, overall shape is identical, right? It goes down, it has a derivative of 0 at the origin point, and then it shoots back up. So all you want to check here is the end behavior. This x to the power of 4 term will basically dictate how things go at positive and negative infinities. This will grow or shrink far more than any of these terms will when we get to very large or small numbers. And as you can see, the default is that when we go to infinity, this goes to infinity. When we go to negative infinity, since the power is even, the function will go to positive infinity once again. So I'll show you the 4 different types of quartic functions. This is the first type. Let me erase this. This is the second type. This is the third type, and this is the 4th type. So we have 4, and I'll explain why they look like this. Okay, so the first type of quartic function, as you can see, we have 3 points where the derivative equals 0. And if you look at the derivative is a cubic function. So a cubic function will have at most 3 different roots. So in this case, if we draw the derivative directly beneath our function, this is a very good strategy, especially for complicated problems where you're dealing with both the derivative and the original function and what's the relationship between them. It's always a good idea to draw the derivative like below the function to see where its properties align. Here, our derivative, the sign of the leading coefficient will match the sign of the leading coefficient in our quartic function. So it's going to be a cubic function with a positive leading coefficient. So here, we're going to have a 0 here, here, and here. So that means our cubic function will basically look like this. Go up, down, up. And as you can see, the derivative, if we check the signs, negative, decreasing, that's good. Positive, increasing, negative, decreasing, and positive, increasing. So all the signs match each other exactly. How about this case? Here, there are 2 places where the derivative equals 0, like here and here. So what will our derivative look like? If we draw the dotted lines down, our derivative will basically look like this. Now remember, the derivative goes from negative to positive. It goes from decreasing to increasing at this point. but it goes from decreasing to 0 to decreasing again. So it goes from minus to minus at this point. That means, although we start out from negative infinity, our cubic function does not cross the x-axis here, right? It has to just be tangent to it and then go back down to negative infinity and go back up here. So that is what our derivative will look like, because our sign will be negative, negative, and then the only negative to positive change occurs at this point. Okay, how about this type of curve? I'll sort of redraw it so you see what it looks like. This isn't symmetric. As you can see, this part sort of looks like a part of a cubic function. But what you'll notice here is that the derivative never becomes 0 at any part of this curve. The only 0 derivative happens at the very bottom, like that. So the only root of our cubic will be at this point. Now here you can see there is sort of a local, I guess you can say a local maximum of the curve, because before this point, the curve gets, the derivative gets more negative and steeper. It gets the shallowest here, and then beyond this point, it starts to get steep again. So our cubic function will reflect this. We have a very negative derivative up here, but then it starts to get less negative, but even more negative. Then around here, it starts to get less negative. So at that point, we'll probably have a local maximum, but that won't be touching the x-axis at all. So we'll have something like that, and then it will go down, and then it will go up exactly at this point. So we go from negative to positive. So derivative, the function goes from decreasing to increasing at this point only. Our final type of quartic function is one that looks exactly like, well, not exactly, the curvature is different, but one that is symmetric about its like bottom vertex point. Here also we have a derivative of 0, but the key fact is that the function is exactly symmetric, while our number 3 option was not. So if our function is line symmetric here, then our derivative, as we discussed last time a little bit, I think, must be point symmetric, right? Because it has to have the same derivative on this side as this side, but only the signs will be different because you're flipping it across a vertical line. So here, our cubic function will actually look something like this. Or perhaps maybe there's a derivative of 0 here, but that we don't know. Okay, so these are our 4 major types of quartic functions. Now, depending on what your derivative is, this shape, for example, might be flipped. We might have a function that looks like this, depending on where the cubic function exactly lies. Or if we have a negative leading coefficient, our entire curve might be flipped. But the curvature and the location, the style of curvature will remain consistent, right? There's a local maximum here, derivative of 0. Here, the derivative will be 0, but there's no local maximum or minimum. So these are the 4 types of curvatures that you should know about quartic functions. And they all rely heavily on what the derivative is and what the derivative's relation to the x-axis is. If you have 3 roots, then the curve will look like this. If you have 2 roots, like this, 1 root, it could look like this or like this, if it's perfectly symmetrical here. Okay, I want to talk to you a little bit more. Before I talk to you about the geometric ratios, let's practice setting up some quartic functions. How about this? If we have a quartic function like that and we're given all the roots, 1, 2, 4, 6, then we can simply set it up as, hey, k times x minus 1, x minus 2, x minus 4 and x minus 6, where k, we know it's a positive number because the end behaviors were pointing towards positive infinity. How about we have a function that is tangent here, let's say at -2, and this is like 3 and 5. What will this function look like? Well, k times x plus 2, but it curves away, so it jumps back. That means it's an even coefficient. Now, if we write anything above a2, then we won't have enough degrees left, right? This has to be squared in order for us to have enough degrees left in our equation to actually make a quartic function. So you got a function like this. How about, let's try a negative leading coefficient. So it's tangent right over here, and this is negative, let's say this is 0, and this is 3, okay? Here, we'll have k, and we know that k is negative this time. X, now is this x to the power of 1 or x to the power of 3? If the derivative is 0, then it has to be 3 or above, but it can't be 5, obviously. So we have to put in x cubed. Remember, the difference between a simple root and a multiple root of an odd multiplicity is that a simple root will not have a derivative of 0, but a multiple root of multiplicity 3 and above, that is odd, will have a derivative of 0 at the root. So x cubed times x minus, this should be, not here, this should be 4, let's say, x minus 4. And that is how you would set up these quartic functions. If you move these up, right, if the reference line is like something like y equals 5, then you simply add a plus 5 on top of that. So everything else is the same. The attitude that you should treat these quartic functions is the same as that you would treat the cubic functions. But notice that there are 4 types of curvatures instead of 3. Okay, so now I'll erase this and I'll tell you more about the geometry of quartic functions. And yes, there are 2 types of ratios that I want you to know. So remember, for cubic functions, there was the 1 to 1 to 1 to 1 and the 1 to square root of 3. For quartic functions, there are 2 types of ratios I want to show you, and the first one is actually 1 to 1 to 1 to 1. So a quartic function also has 4 equal increments, and I'll show you how. Okay, let's talk about 1 to 1 to 1 to 1. This is about a quartic function type 2 or 3 curves, okay? So here's a type 2 curve, or, okay, I'm going to start with type 3 because that's a little bit easier to model. Okay, my ratios are probably going to be off, but here is what I'm saying. I'm going to grab this point, so the exact point where the derivative equals 0. I'm going to grab the tangent line at the point of inflection. So I told you last time that the point of inflection, you should treat it as a geometric indicator of where the curvature changes. In a full calculus class, you would be more specific with the definition and you would say, hey, you're going to find like the local minimum and maximum of the derivative. But as you can see, you can interpret that geometrically as well, right? So here, the curvature changes at this point and at this point. And that's because, hey, you're getting steeper and then you're getting less steep. So the curvature kind of transitions at this point. But here it's quite clear, right? The derivative is very steep, then it gets the shallowest at this point, and that follows the derivative, of course, and then it gets steeper again, and then it gets shallower. So the inflection points of inflection are here and here. For this function, it's here and here. So it goes like that, and there's one more point here where the curvature changes from getting more steep to less steep. But I don't think that's a big thing to worry about for now. But for this 1 to 1 to 1 to 1 ratio, you want to grab the tangent line right at the point of inflection. So sort of like that. Okay. And then your third point is going to be the local minimum point, or the curve right over here. And then your final point is going to be this point. Okay. Oh, sorry. Your third point is actually going to be on the point of inflection. So you have 4 different segments. And turns out this segment length and this segment length and this segment length and this segment length are all equal to each other. Okay, so if you want a proof of that, we can set up an equation quite simply. So let's say that let's set up our coordinate system so we would have to do the least amount of calculations. Let's say this is 0, and since we know, well, this is the result, but let's say for the convenience of calculations, this is 4 alpha. Our quartic function will be y equals, let's call the leading coefficient k, x cubed times x minus 4 alpha. So that's going to be kx to the power 4 minus 4k alpha x to the power of 3. Y prime is going to be 4k x to the power of 3 minus 12k alpha x to the power of 2, which is going to factor into x squared, 4k x minus 12k alpha. And that has to equal 0. X equals 0, or x equals, so here you can basically get rid of the case because this is going to be equal to 0. 4x minus 12 alpha equals 0. X equals 3 alpha. So there we go. Our local minimum is going to be at 3 alpha. And then to get the inflection point, remember, it's kind of a preview of what we call the second derivative. Don't worry about that. But in order to find this point is exactly going to align with the local minimum point of this cubic function, right? Because it's going to get steeper, then it's going to get less steep. So try to interpret it geometrically. But in order to find that, we're going to have to take the derivative of f prime and find the second point there. So f, we call this y double prime, but you don't have to worry about the syntax again. This is not our main focus, but for the sake of the proof, that's going to be 12x squared minus 24k alpha x. So that's going to equal to x times 12x minus 24. Oh, sorry, did I forget the k? 12k. 12kx minus 24k alpha. So this has to equal 0 because x equals 0 is pretty obvious. If we divide both sides by 12k, we're going to get x equals 2 alpha. Okay, to prove our final point, the intersection of the tangent line from here and the x-axis, we need to set up the tangent line. Okay, so this is 2 alpha comma. If we plug this back in here, 2 alpha comma, this is going to be k times 8 alpha cubed times, what's 2 alpha minus 4 alpha? Negative 2 alpha. So that's going to be k times negative 16, so negative 16k alpha to the power of 4. Okay, so this is going to be negative 16k alpha to the power of 4. And then we can set up the tangent line. We know that what's y prime of alpha? Y prime of alpha is going to be 4k alpha cubed minus 12k alpha cubed. So that's going to be negative 8k alpha cubed. So our equation L, let's say, the tangent line L is going to be y equals negative 8k alpha cubed times x minus 2 alpha plus our y value was negative 16k alpha to the power of 4. And then we can set y equals 0. This has to equal 0 to find the x-intercept. 16k alpha to the power of 4 equals negative 8k alpha cubed times x minus 2 alpha. So here, 16, 8, this will be 2. We can fire off the k's. We can also fire off alpha cubed to alpha to the 1. So 2 alpha equals negative, so we can put this negative sign back here. 2 alpha equals, did we do that right? Oh, we forgot this, negative 16k alpha to the power of 4. So this will go to 1 and this will be 2. Yeah, okay, so we need to include that last term, sorry. So this distributes here, 2 alpha equals 2 alpha minus x, and that will be, we ran off the k, alpha to the power of 3 will be gone, so that's minus, oh right, so this is negative 16. Oh, never mind, wait. So we move this over to the right-hand side, right? Negative 8k alpha did we calculate this correctly? 8, I don't think this number is correct. If we plug in 2 alpha, this will be 8 alpha cubed. 8 times 4 equals 32, minus 12 times 4 minus 48. So 32 minus 48 is going to be negative 16. So this should be negative 16 here, here, and here. Okay. Negative 16, so we can completely wipe that off. So alpha equals 2 alpha minus x would be our final equation. So x has to equal 2 alpha minus alpha alpha. Therefore, our x-intercept of this tangent line has to be alpha. And there you go. 0 alpha, 2 alpha, 3 alpha, and 4 alpha would be the ratio. And this is true for every single type 2 curve. As you can see, the proof is pretty messy, but we selected the best possible coordinate system to prove it in. So this much algebra would get you this pretty beautiful ratio, in my opinion. Okay, so I'm going to show you how that extends to type 3 curves as well. So for a type 3 curve, your curve would look like that, right? And then here is your tangent line from this point of inflection. And here would be your tangent line from this point of inflection. Sort of like that. Remember the concept of our difference function. If we subtract this black line from the quartic function, we'll get a type 2 curve, right? You don't have to assign names to them, but since I drew them in this order, I'm just referencing them for your convenience. So if we do, let's say fg, if we do f minus g, subtract the linear from the quadratic, then our curve is going to look like this. It's going to have a derivative of 0 at this point, and then it will go down, and then it will go up like that, right? This point falls here, so 1 to 1 to 1 to 1 is still going to hold as long as I draw a parallel line here. And the y-coordinate, well, I don't necessarily need to draw a parallel line down here, right? As long as I draw a parallel line up, then this ratio is going to be 1 to 1 to 1 to 1 just fine, okay? Because we know that if we make similar triangles here, this base ratio is going to be 1 to 1 to 1 to 1 due to our difference function being the type 2 curve that we already proved it on. So yes, this is pretty far-reaching. I don't think you'll see that many quartic problems that use this ratio, but it's always, I think this is a thing worth remembering when you're dealing with polynomial curves. Okay. Can I fit the last property here? I'll try. I'll make an entire board on quartic functions. Okay, the second ratio that I want you to remember is 1 to square root of 2. And this applies to type 1 curves, okay? 1 to square root of 2. Remember, in cubic functions, there was a 1 to square root of 3 ratio for a line going through the point of inflection, right? But here it's a 1 to square root of 2 ratio. And I'll start with a very simple type 1 curve. And then we'll use the difference function to generalize that to the type 1 curve. The simplified version is where I have a curve that looks like this. The two local minimum values are going to be equal to each other. And I'll draw another line on top, like that. Here, I'm going to mark my local minimum points. And here's where the 1 to square root of 2 ratio kicks in. I'm going to start from the middle of this point, of this local maximum. And then 1 to square root of 2 would be the ratios of the horizontal distances from here to here. Okay? All right, if we try, we'll try to prove it again using our coordinate system. So where would be the best place to place our coordinate? Here, I think we're going to start off with this being our x-axis, and let's put a pause on where our y-axis will be because I want to show you something. Let's call this negative let's set it up this way. Okay. The derivative of this quartic function is going to be a cubic. So if we draw the cubic derivative here for a sec, right? It's going to go from negative to positive and then positive, negative to positive and then from negative to positive again. And here it's going to go from positive to negative. Okay. Actually, I might have a simpler way of doing this. Okay, I think this will work. So we gotta place our coordinate system very carefully so that it takes the least amount of algebra to prove our point. I think let's set up the coordinate system so that these 2 points are negative alpha and positive alpha, where alpha is a positive number. How's that? And we'll use algebra to see where this x coordinate is, because having negative alpha and positive alpha here gives us enough information to actually set up the entire equation of the quartic function. Why? Because we can set a arbitrary leading coefficient for all possible leading coefficients. K is positive. And then we can say, hey, x minus alpha squared, because we formed the quartic function, right? Power of 2 and power of 2. So this is our equation of the function, but if we say x plus alpha x minus alpha is x squared minus alpha squared, we can simplify it further to x squared minus alpha squared squared. We're going to take the derivative y prime equals, now use the chain rule, 2k times x squared minus alpha squared, and then the derivative of the inner function is going to be 2x, right? So we have 4kx times x squared minus alpha squared, and that has to be equal to 0. So either x equals 0 or x squared minus alpha squared equals 0, and this equation has the roots plus minus alpha. We know that at alpha and minus alpha, the derivatives are 0, but the other root that we're looking for is actually x equals 0. So this coordinate is actually 0. So if we draw the common tangent line from negative alpha to alpha, the local maximum will have an x coordinate of 0, which means that even if these are arbitrary numbers, the local maximum point will always be the midpoint of these two points. Okay, so that's the first thing that I wanted to prove. The local maximum happens at the midpoint of these two tangent points, and that's always true. Okay, now let's get on to proving this guy. Okay, what might be a good way to put this? I think now we'll switch up our coordinate system so that our origin point lies exactly on the local maximum point. And we're going to still assume that this it has an equal local minimum. It has equal local minimum values, so like that. Okay. Now we now know that the curve is going to be symmetrical about both of these points. So I think we'll do the setup the same way. Yeah. Should we go from here to here? How's this? We figured out that the local maximum is the exact midpoint of these two, right? So in this case, where both of them are tangent to the x-axis like this, the entire function is symmetrical about this line going through the center. Why? Because if we plug in negative x instead of x, the expression will not change one bit, right? Because negative x squared is equal to x squared. So since we chose these arbitrary coordinates and we showed that it's symmetric about this center line, then any function should be symmetric about the center line as long as they have equal local minimum values. So that means that this particular function that we have right now is an even function, and we can arbitrarily set, hey, this is alpha, this root is alpha, then this root is going to be negative alpha. And now we can set up our equation. Y equals x plus, let's say k times x plus alpha, x minus alpha, and then our this has a multiplicity of 2, right? Because it has that going up there, just touching it, and going back shape, x squared. So that's going to be our function. And we can simplify that to kx squared times, let's use the x squared minus alpha squared, which is equal to k times x to the power 4 minus k alpha squared x squared. Now we're going to take the derivative. 4kx cubed minus 2k alpha squared x, right? Right. And then we're going to set it equal to 0. Since we know that obviously 0 is not a solution that we want, we can divide both sides by x, and then divide both sides by k, and then divide both sides by 2. So we got 2 times x squared equals, so everything is gone except alpha squared. So x equals 1 over square root of 2 times alpha. So if this is alpha, then, oh, sorry, I forgot the plus minus. Plus minus 1 over square root of 2 alpha. This is going to be 1 over square root of 2 alpha, and this is going to be negative 1 over 2 square root of alpha. So these points right here. That means that if we multiply this line segment by square root of 2, then it's like multiplying 1 over square root of 2 alpha times square root of 2, and that will get us exactly 2 alpha, which completes our proof that this ratio is 1 to square root of 2. So we realized a couple of important things here. First of all, if a quartic function has the same local minimum values, then it's going to be perfectly symmetrical about its center line, which also happens to be at the point of the local maximum. Second of all, if that is true, then these two line segments will have a distance ratio of 1 to square root of 2. Now, how about type 1 curves that don't have the same local maximum and minimum values? Well, we can still transform them, right? Because now we know, we're pretty comfortable with the notion of difference functions, right? If we have a quartic function that doesn't have two local minimum values that are identical, we can take the common tangent line, right? So we can take the common tangent line here and draw a parallel line down here. And once we take the difference between, like, we can do f minus like g right over here, right? So if we do f minus g, then we're going to get a specific type of curve where our quartic function is going to look like this. Obviously, the ratio here is kind of off right now, but if we take the difference function f minus g, that means all the ratios that we've calculated will hold for this function, right? 1 to square root of 2, like that. And that will directly translate over to our original function. So if we draw like a vertical line there, that should match up exactly. This would be 1 to square root of 2 in this fashion as well. So everything does really translate nicely if you think about the difference function between the quartic and the common tangent line and the upper tangent line here that is parallel to the common tangent line. Yeah. So again, that's a lot of content for quartic functions, but all of these proofs are to say that, hey, it's going to give you quite a bit of convenience, and it will save you quite a lot of like algebra and calculus and trying to figure out the derivative and setting that derivative equal to 0 and trying to solve like cubic equations and all that. Okay. Yeah, so I think that's all you need to know about quartic functions. The rest, as you work through the notebook, we'll go through together. So let's go over a few more questions on the workbook, and then we can call it a day, I think. Okay, so I'm going to erase this board, and then we can wrap up with the workbook. So as you can see, even though these are polynomial functions of degrees like 3 or 4, it is a lot more complicated to analyze compared to, like, say, parabolas, right? There's a lot more curvature options, and you have to consider a lot of stuff. You have to consider what their derivative is, and if it changes from like positive or negative, what's the sign of the derivative, right? But this analyzing in this way using calculus is going to really set you up for even more complicated functions. You'll struggle way less getting adjusted to those than someone who would be doing this for the first time. So let's build up our skills now. So calculus will be more enjoyable, right, and less daunting when you take the full course. Okay, so I think we ended off at number 11. Number 12. Okay. Find the range of constant a, so that function x to the power of 4. So we're now getting a quartic function. Plus 4x cubed minus 4a x squared has a local minimum value. Okay, so remember the curvatures that we just covered. So remember, we had 4 different types. One with 3 different local extrema, one that looks like this, one that looks like this, and one that looks like this. We must have a local maximum value, which means that what's the only type of curve that has a local maximum? It's only this type of curve, right? And in order for our quartic function to look like this, how many points should the derivative equal 0? 3 points. So what we need to do is we need to take the derivative to further analyze this. F prime of x equals 4x cubed plus 12x squared minus 8ax. And let's set that equal to 0. Fortunately, we can group out an x, so that might lead to a discriminant question, right? 12 minus 8a. On second thought, we could have also pulled out a 4, right? Then this will be 3. Like that. Okay. We know that x equals 0 is going to be a root. That's great. What we need to confirm is that this must have 2 roots, right? Because we need 3 different points where the derivative equals 0. That means we get to use the discriminant. We'll use regular d, 9 minus, that's going to be plus 8a. And that has to be greater than 0. Is that all? So a has to be greater than negative 9 over 8. But there is one more thing that we should think about. Now, we're analyzing a cubic equation, right? So we're analyzing a cubic equation. That means that we need 3 different roots. Now, x equals 0 becomes a problem if one of the roots of this quadratic equation is also x equals 0. That means that we won't get 3 distinct values of x. If we plug in x equals 0 into this quadratic, that means we only get 2a, negative 2a, and this cannot be a root of that quadratic, because then we'll get multiple roots of 0, and that's not what we want. So the added condition is that a cannot be 0. So watch out for those little things, right? This is the main problem solving part, using the discriminant, but also checking that, hey, a 0 can't be a root of this quadratic is also equally important, because that is the full answer. Okay. Number 13, it's about analyzing the derivative, right? So what can the derivative tell you about the function? I think we talked about that quite a lot. So I'll leave that for homework. Number 14, also, I'll leave that for homework. Okay. I'll leave number 15 for homework as well. I want you guys to become more comfortable with analyzing these graphs. Okay. Number 15 and 16, I will leave for homework. I want you guys to really try and solve these questions, especially number 16. I want you to get accustomed to dealing with these situations. Number 16 says cubic function. I think I fixed that in your workbooks. It should say a monic cubic function. So if it doesn't say that, you can add that to number 16. Let's see here. So number 16 should say, oh, I didn't put that in. Okay, so that's a typo. It should say you should add the word monic cubic function f of x. So it has a leading coefficient of 1. Oh, never mind. It's already fixed. Okay, it has a leading coefficient of 1. Okay, I got confused. So it's already in there, so you should be fine. Look at those 3 conditions carefully and try to remember in the Unit 1 exam on the final problem, we did a variety of test cases for that like shifting continuity problem. So it's really important to think about what might work and what might not work. And will this work? Well, I need to verify this case and then I will need to verify that case, okay? The problems are going to get harder. And as the problems get harder, I want you to have more time. So allocate yourself a bit more time to solve these questions, okay? And like solving problems through persistence, and really, even if you can't solve the problem, sitting through it and thinking about different ways I might tackle this problem is really, I think, good practice. So your homework for this chapter, 2.3 for this week, is 3, 4, 6, not 5, 3, 4, 6, 7, 9, 11, 13, 14, 15, and 16. And we'll stop at 16 for this week. Okay, great job following along today. So I think, yeah, there's a lot of content to know about like both cubic and quartic functions, but as you solve these problems, you'll get naturally more comfortable with dealing them, and then we'll solve a lot more problems involving them in the future, so you can really get familiar with how do I analyze these functions to solve problems, okay? So that's your homework, and I'll see you in the next session. Okay, goodbye.